All right, so we're going to start talking about angular projectiles. This is the last one of the projectile parts. For the most part, it actually doesn't change much from what we've already talked about with vertical projectiles and horizontal projectiles. There's just one little addition, and that's the fact that the object is now given a velocity that is not purely in the vertical or horizontal direction. So just like with the horizontal projectile, we're going to once again have to use an XY chart in order to organize what's going on in the X direction, what's going on in the Y direction. However, unlike last time, we're not going to have a velocity on one side and an initial velocity of zero on the other side. There's going to be a velocity on both parts. So what this is going to force us to do is we're going to have to split that initial velocity that they tell us, because what they're going to say is that an object was shot with some velocity at some angle. Just like with the forces, we can't deal with things that are at an angle, so we have to break them up into components. So we're going to have to break our velocities into an x and y component, and then after that, it basically ends up working the same way as we've done with stuff with the horizontal projectiles. The other thing to keep in mind is it is also sort of a vertical projectile. So things like what's going on at max height, those hidden terms, they still apply. If you recall, with the vertical projectiles, we had that phrasing that when an object's thrown in the air and when it reaches its maximum height, its velocity at that point is zero. We still have that same concept, but keep in mind it's only going on in the vertical direction. So what we can do is we can actually treat the y side as if it was a vertical projectile, and then the x side acts horizontally. Now, if you're kind of thrown for a loop here, that's fine. We're actually going to be doing a lot of this stuff in class. What we're going to talk about right now is just practicing breaking up velocities into x and y components. So once again, just like the last video, there are going to be a few practice questions that I'm going to throw in. We're not going to do anything that's really angular projectile related, but it's more of what you are going to have to end up doing eventually. These questions are not in the notes, so you'll just do it off to the side. But once again, I will actually return back to some note questions in the end. So here's the first question. I just want to know what are the components of this velocity at that angle. So pause video, works up. We'll move in a second. All right, so we have 30 meters per second at an angle of 20 degrees. Just like we've done previously, because that velocity is that angle, I should say, is next to a horizontal line, it's to the horizontal. That means what I can do is just say that the x side is cosine and the y side is sine. I don't draw a little diagram here, but if you make a right triangle, the bottom angle is going to be 20 degrees. The x side is cosine because it's adjacent over hypotenuse, and the y side is going to be opposite over hypotenuse, so that's going to be sine. You can use it, your little right triangles and derive cosine and sine, but honestly, it's going to save you so much more time to just kind of get used to memorizing that horizontal components are going to be blank cosine and vertical components are going to be blank sine, as long as this angle is to the horizontal. You would never see this where they gave you an angle to a vertical in the angular projectile questions, but keep this in mind in future cases that there are times you've seen them in the force problems where they give you angles relative to a vertical line, in which case, if you want to keep with that same idea of saying every x component is cosine and every y component is sine, you might want to find the complementary of that angle before you continue. But in this case, you don't have to worry about that. So again, Vx is V cosine theta because that's how components work. It's whatever we're finding the component of, in this case V, times cosine of our angle. That's the x component. So it's 30 cosine 20, and you get 28.2 meters per second. For the y, it's going to be sine, so do the same thing, but with sine instead of cosine, and we get 10.3 meters per second. All right, roughly about the same. Make sure that you are in degree mode. All right, here's the next question. Pause the video, work itself. We'll go in a second. All right, so again, plug in our numbers, and we end up getting 7.5. It is very useful. You don't need to memorize anything with sine and cosine values. However, it is very useful to keep in mind what sine 30 and cosine 60 is. A lot of times, Regents and AP questions tend to try to use numbers. I said this before, they tend to try to use numbers where you should be able to find the cosine and sine easily. Like you should be able to do the math without using a calculator. So they tend to use things like sine 30 and or cosine 60. Like they use those angles a lot. Sometimes they do sine 37 or cosine 37 in order to deal with like 3, 4, 5 triangles. But those two are really easy because they're zero point 0.5. One reason why I mentioned that you want to keep them in mind is because I know a lot of times your calculators tend to be in radian modes, and probably one of the biggest issues with this is that people forget that they're supposed to be in degree mode. They do the whole problem in radians, they get crazy numbers, don't really realize, and they just keep going on. Sometimes it's easy to check because if you're in radian mode, there's a good chance your answer is probably going to be negative. And if you see a negative number with any of these component questions, as long as this angle is less than 90, it doesn't make sense. So that's usually a big red flag that something's wrong. But that it doesn't always end up being a negative, which is why you kind of want to be careful. So keeping in mind that cosine 60 is zero point 0.5, sine 30 is zero point 0.5 is really useful because when you do a calculation like 20 sine 30 and you go, wait a minute, this is supposed to be zero point 0.5 times 10, times 20, that should be 10. What's going on? So it can help you save you in future problems. Just going back, we do sine 60 for the y component, and we get 13 meters per second. All right, here's the last one. Pause video or self. We'll go over in a second. All right, again, nothing crazy. We get 4.37 in the x and 3.66 in the y. All right, like I said, I just want to do 3 really quick practice questions of finding components just because I want you to be aware that this is something that you're going to have to do. This is almost going to be an immediate reaction. When you do an angular projectile, you're going to see that velocity, you're going to see that angle, and you should immediately jump into doing this. Finding the x component, finding the y component. I forgot to make these y. Whatever. You're going to find them right off the bat before you can continue on. Once you do this, just like with the forces, once you break it up, these velocities into components, these numbers do not appear in your chart ever again. They disappear. They're gone in the ether. These are the only numbers that I now care about. Again, there's no point in me finding the components if I'm not going to use it. That's one big issue that I see people do is sometimes they remember that they have to do sine and cosine with these numbers, but then when they go to plug numbers in the chart, they kind of throw out and they just go back to using the 5.7 number. Maybe they use one of these, but they don't end up using both of them, and it ends up being a big issue. If I'm telling you to do the components, it's because you're going to use these components. Again, there's very few times where you're not going to end up doing this right off the bat. All right, and that's pretty much it for this part. Now, in class, like I said, we're going to go into a lot more detail about breaking down the problems, setting them up, and we'll do some practice problems there. There'll also be another video where I'll just do a few practice problems as well. But what I want to do here is actually fast forward a bit and go back and talk about the factors that affect angular projectiles. So this is something that that's important with projectiles in general. You should know what factors can be changed that would affect the projectile. Again, just like the horizontal projectile, we talked about how changing things like height and the initial velocity would affect the time and range in the air. We kind of want to do the same thing here. So the height is an easy one. It actually works the exact same way as the horizontal projectile. So I forgot to mention. So increasing the initial vertical velocity will increase how high it goes in the air, as well as the time of flight in the air. Um, I didn't put it here, but this is something. So there are things like the height that ends up like the starting height. As you can probably guess, if you start off higher off the ground, it's going to be in the air longer than when it goes to land. And because it's in the air longer, it's going to reach a longer range. I already wrote the initial vertical velocity. Increasing that will end up making it so that it's both in the air longer, reaching a higher height, going further. Um, the increasing the horizontal velocity is going to make it so that it just reaches further, but it doesn't change the max height or time in the air. However, so a lot of that stuff kind of carries over from the horizontal projectile. However, one thing to keep in mind is the angle. The angle is actually a big factor. How does changing the angle affect things like range and time in the air? So if you want, you can actually follow this link. Go to the website. It's called fet.colorado.edu. It's a really fun website. It's got all these simulations that you can play around with and do stuff. There's one with a angular projectile and this cannon, and you can move the cannon around, change it at different heights, change the angles, yada yada yada, and see how ranges go. And the big questions that you want to ask yourself are things like, what angles give the greatest max height, the greatest range, and the same ranges. So pause the video, try to see if you can answer this yourself. You can play around with this before you coming back. I'll give you a second. All right. So, what are the angles that give you these big values? Well, the angle that gives you the greatest max height is very easily 90 degrees. Makes the most sense. If you want it to have the be in the air the longest, you want to shoot it straight up. There's no point in shooting it off at an angle because some of that velocity is now going to be pointed to moving it horizontally instead of vertically. You want all your velocity to be vertical upwards, so 90 degrees is the best. What angle gives you the greatest range? As long as you're shooting it from the ground and you're going to the ground, the greatest range occurs at 45 degrees. Interesting side note is that if you raise the object so it becomes an asymmetric projectile, it starts off at a higher height. 45 is no longer the greatest range. It actually decreases. So the higher up you go, the lower that max angle actually goes. Uh, Interesting side question to think about is why that happens. And then the angles that give the same range, it turns out complementary angles. Again, this only really applies to surface projectiles, symmetric projectiles, in the sense that it starts at a height and lands at the same height. But any two angles that add up to 90 degrees will always give you the same range. So 30 and 60 degrees give you the same range. They have different times in the air, they have different max height values, but they both land at the same spot. Uh, 90 and 0 land at the same spot because they both add up to 90. And it also explains why 45 is the max range because there is no other, like 45 is its own complementary angle. So it's by itself. Interesting thing to think of. You keep that in mind that when you deal with these problems, that as you increase the angle, you should know how things like max height, range, and time in the air all change. So the max height increases as the angle increases because it reaches that max at 90. But range, on the other hand, will increase to a point and then begin decreasing. It starts coming back. If you've ever played with a hose in your house, you've probably seen this before. All right. And that's pretty much it for the angular projectiles, at least what we're going to talk about in this video. Like I said, in class, we're going to go into a much bigger deep dive of going over practice problems. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.